Good day, everyone. We are reviewing Wetzel's Limnology textbook, edition number 4, chapter 5, and we are in subchapter 2, catchment structure and runoff generation. A. Catchment concept and delineation. A catchment, also termed watershed, drainage basin, or drainage area, is defined as a topographical delimited area that gathers and transmits water from a higher elevation site and transports this water to a designated downstream location. Catchments are separated from each other by topographic divides such as ridges, peaks, and saddles. Mountainous catchments typically comprise steep upland slopes which supply water, sediments, and nutrients to lower lying areas and floodplains as runouts, accumulations, and depositions. The catchment structure is typically used to assess material, for example, sediments, nutrients, budgets, in the continuum from hill slopes to channels. The analysis of such budgets allows us to understand the sources, transport, storage, and runoff of materials. Routing and storage of water and sediment from uplands to lowlands depends on the characteristics of channel networks in a catchment. Water and sediment from steep hill slope first flow into small streams called headwater channels. This uppermost area of the channel network within a catchment is their headwater system. A headwater system consists of multiple units, including hill slopes, zero-order basins, and first and second-order stream channels. Zero-order basins or swells have concave topography without defined channels and no perennial surface flow. Other hill slope segments are typically divergent or planar surfaces with no channelized flow. Following the stream ordering system of Strattler, first and second order channels have either perennial and or ephemeral flow depending on runoff generation from hill slopes and bedrocks. Other channels ordering systems have been developed. See Chapter 4. And ordering also depends on the resolution of maps and whether only perennial channels are included in the assessment. Some later hydrological and geomorphic studies suggest that the relative upper size limit of first-order streams is likely 1 kilometer squared. Water and sediments are transported from headwater systems to large water bodies such as lakes and rivers, depending on the connectivity of hydrological processes within catchments. Related to the transport of such materials within catchments, connectivity from upstream to downstream is important, as explained by the river continuum concept. Furthermore, connectivity from numerous tributaries to main channels, including the presence of floodplains and alluvial fans within channel networks, is a key geomorphic component that alters water and sediment dynamics. Hence, hydrological processes from hill slope to channels that define the headwater area vary depending on vegetation, geology, and salt formation. Such differences alter the order of magnitude of connectivity within catchments. Drainage patterns represent key structures of catchments. Drainage patterns depend on geologic structure, rock types, tectonic activity, landform shapes, and anthropogenic alternation. Dendritic pattern is a typical channel network in a relatively homogeneous geology of where geology exerts less controls, whereas non-dendritic drainage patterns, so for example trellis, occur in areas underlain by different lithologies and tectonic activity. Such network structures alter the timing and accumulation of runoff, sediment, and nutrient transport from headwaters to lakes. For instance, the mobility of mass movements, landslides, and debris flows is affected by tributary junction angles. Thus, the location of lakes and ponds within catchments with respect to the channel network are important for understanding routing and storage of water and sediments, as well as for examining human impacts on lakes and ponds. Furthermore, locations of dams and reservoirs that control water and sediment movement need to be considered as key components within catchments. B. Flow evolution and from hill slope to catchments. Hydrologic and geomorphic processes are closely coupled from hill slopes to stream channels within confined and steep valleys of headwater systems. Storm flow generation in headwater channels is affected by the degree of soil saturation in hill slopes and zero-order basins and by changing antecedent moisture conditions. Such dynamic changes in soil moisture and runoff associated with rainfall is called the variable source area concept. This conceptual framework describes the expansion of source areas for rapid runoff occurring from onset of rainfall to later periods when soils are saturated. During dry conditions before rainfall, stream flow is usually generated by subsurface flow or bedrock flow. This is termed base flow. In dry conditions, rainfall typically infiltrates into the soil matrix. Occasionally, HOF occurs during intense precipitation. Pore spaces in the soil, both large and small, play different roles in relation to water supplies by rainfall. In the early stages of rainfall, water is stored in small pores between soil grains. In this state, water is present in some parts of the soil termed the unsaturated state. Unsaturated water is retained in the soil or flows slowly within the soil matrix under an energy gradient. When precipitation continues and sufficient water accumulates in the soil, water flows into and out of large pores, causing drainage. The rate of water movement in the saturated state is 100 to 1,000 times faster than in the unsaturated state. As rainfall proceeds, subsurface flow within the soil matrix emerges at the foot of hill slope and in riparian areas, gradually increasing with increasing wetness of the basins. When subsurface water reaches the stream flow begins to increase. Concurrently, surface runoff also initiates in some ephemeral channels. With increasing wetness in catchments, zero-order basins accumulate water initially those with relatively shallow soils start to contributing to surface runoff. As more water accumulates, zero-order basins with deeper soils contribute to surface runoff. Preferential flow from hill slope also augments storm flow once the threshold of soil is reached. So why don't we look at those two figures here? Figure 5-3, so conceptual view of flow process evolution from hill slope to catchments. During dry condition, riparian zone and direct precipitation on channels are the only active sites of flow generation. Through flow from the soil matrix on the foot of hill slope and riparian areas gradually activates with increasing wetness. Zero-order basins with relatively shallow soils, dark shaded areas, begin to contribute surface runoff, large arrows, during wet conditions, whereas preferential flow, small arrows from hill slopes, contributes less to stream flow. Flow begins to occur in transitional channels emerging from zero-order basins during wet conditions. Zero-order basins, including those with deeper soils, lighter shaded areas, and preferential flow, actively contribute to storm flow during wet conditions. So this is a dry condition. This is an ephemeral stream channel and a perennial stream channel. So ephemeral means that it's not flowing the year round, where perennial is flowing year round. This is the same channel here, and we are dealing with zero-order channel as per the figure legend here that we just read. So we have riparian zone, which is pretty much vegetation around the stream, and then you can see it's starting to get wet. So therefore, the riparian zone is widening. And then we have a wet kind of environment where it has rain a fair amount and zero-order bases with shallow soil. And so we are starting to see some surface flow here. And then this is a very wet environment where you see a lot of contribution to the stream in the where the soil is dry, and then of course contribution at the surface level for very wet soil here. And for the gray area, the lighter shade area, including those with deeper soil, and preferential flow actively contribute to storm flow during very wet conditions. So here we also have contribution from this deeper soil to the surface and to the stream itself. So here, figure 5.4, we are about to embark actually in the water balance of a lake. We are looking at various inputs and outputs. So the inputs are in blue, and then the outputs are in orange-red. So inputs are precipitation. We have groundwater in groundwater seepage. So GW in here. So where groundwater is seeping into the lake. And then we have QIN, which is stream flow input to the lake. And then we have RO, which is catchment runoff. Okay, so where we have like some surface flow that is providing some input to the lake. And then in outputs, we have E for evaporation, groundwater out, so we have some loss of groundwater to groundwater. And then we have Q out, so we have a stream that is draining the lake, and this is Q out. So let's continue here. Ephemeral channels emerging from zero-order basin typically have high flows during major storms preceded by very wet conditions. Some of the soil water percolates into bedrock and is stored for longer periods. In such cases, the presence of a soil layer allows water to flow slowly through the soil and promotes infiltration into the bedrock. Runoff generation from areas of exposed soil or bedrock caused by anthropogenic or natural disturbances, for example, soil displacement during earthquake-induced landslides, also should be considered as variable sources for a more comprehensive understanding of runoff generation in catchments, because significant changes in flow pathway may occur. During rain and rain-on-snow events, nearly saturated conditions in hydrologically responsive areas, for example, zero-order basins or swells, may induce landslides and subsequent debris flows. 3. Water balance in catchments with lakes. A. General water balance concept. Globally, more water evaporates from ocean than is returned by precipitation, whereas on land, overall, more water falls as precipitation than is lost by evaporation. A large part of the landfall precipitation originates from evaporation of oceanic water. Massive water demands and diversions for agriculture, urban and industrial development, and land clearing effects, and climate change are creating changes in what would otherwise be a relatively stable global water balance. Furthermore, construction of large reservoirs and other impounded river waters can modify local climates, particularly in dry and seasonally dry regions. A water balance for a catchment of a surface water body, like a lake, can be simply described as water inputs, inflow, equal outputs, outflow, plus changes in storage. For a lake system, the water balance is largely regulated by inputs of stream and river flow, runoff from the surrounding catchments, direct precipitation, groundwater and saltwater seepage, and glacier and permafrost melts, whereas outputs associated with outflow of surface water evaporation, seepage losses, and sublimation. In hydrologically modified systems, water diversions can also significantly contribute to lake inputs and outputs. Changes in water storage require monitoring of lake level changes as well as bathymetry over a designated period. This process can be simplified by conducting the water balance over a period where lake levels are the same at the beginning and the end. Projecting how precipitation timing and magnitude evaporation and runoff will change over several decades can provide insights into how lake water levels might change in a warming climate. A. Inputs. Precipitation that falls directly onto lakes generally contributes only a small input to lake systems. Exceptions include when lake catchment areas are very small and lake surfaces are relatively large. For example, precipitation over the Great Lakes, where the lake areas constitute about 1/3 of the total contributing basin, is the largest input of the water balance. The reliability of precipitation inputs depend on the number and position of gauges around the lake and across the lake surface. Uncertainties in direct precipitation inputs to lakes arise from inadequate gauge coverage and underestimation of rainfall and particularly snowfall catch by gauges, especially during windy conditions. In larger lake systems, advances in remotely sensed data collection, for example, active and passive data from satellites, radar-based precipitation estimates, provide an alternative method for acquiring data over these vast water bodies. Stream and small river flows into lakes often constitute major inputs of water, particularly in small to medium-sized lakes. Oftentimes, multiple small streams enter these lakes, presenting a major effort for monitoring via stream gauging. The largest uncertainty in measuring stream flow arises during large flood events when streams overtop their banks, introducing errors in peak flow estimation. An alternative approach to estimated surface water inputs is to use catchment hydrology models, which require considerable catchment data for calibration. Another input is direct overland runoff into lakes. This will typically not be captured by streams gauges, but can be estimated by process-based catchment models. Assuming that all incoming streams are gauged and or robust catchment model is used, these surface water inputs into lakes likely have the least error of all water inputs. Groundwater seepage contribution into lakes, exfiltration, are difficult to quantify and have largely been either ignored or estimated as a residual in most lake water balances. Seepage into lakes occurs when the lake bottom lies below the local groundwater table. Seepage meters can be used to directly measure groundwater inputs, but only in shallow waters near the perimeter of lakes. And direct methods for estimated seepage have employed isotope balance approaches using oxygen-18 composition of lake water, precipitation, and groundwater, as well as using vertical profiles of radon as a groundwater tracer. Both indirect approaches require rather extensive sampling, employ extensive analytical method, and have limitations related to climate and geological settings. As such, groundwater seepage estimates typically have the highest uncertainty of all inputs. Models of three-dimensional groundwater transport can help quantify seepage. However, hydraulic properties and relevant boundary conditions must be specified. Groundwater springs that enter lakes from surrounding catchments can be quantified as contribution to surface water runoff, either by stream discharges or direct overland flow outputs. Evaporation from lakes constitutes a substantial portion of outputs, particularly in shallow lakes with large surface area to volume ratio. Lakes in dry region with no outlet, closed lakes, lose their water primarily by evaporation. Quantification of evaporation from lakes is typically accomplished using an energy budget approach, requiring meteorological monitoring on and approximate to the lake. Lacking such resources, evaporative losses are estimated as residual in the water balance. Aquatic plants also transpire water from lakes. This process is highly seasonal in temperate lake system, but can persist year-round in the tropics and subtropics, at times surpassing water loss due to evaporation, depending on the level of biomass. Sublimation, the phase transformation of water from a solid to a vapor form, only affects water loss from lakes that are frozen most of the year, for example in Antarctica, where high winds persist. Similar to surface water inflows, outflows from lakes often constitute the major portion of the output budget. Outflows in single or multiple channels can be monitored at gauging stations. Unlike inflows, it is not possible to apply catchment hydrology models to estimate lake outflows. Such monitored flows have a relatively high degree of certainty. Outflows from lakes have direct effects on the water balance given their high velocity in contrast to losses or gains by groundwater seepage. Seepage losses from lakes to groundwater reservoirs, infiltration, typically occurs in dry sites where water tables are well below the lake bottom. In addition to the location of the water table, permeable lake bottoms, for example sandy or gravelly materials, are more likely to lose water by seepage compared to lakes with rocks or clay substrate. Groundwater models can potentially be used to estimate seepage loss with the same constraints as for seepage gains into the lake. Changes in storage. Quantifying the change in lake storage over time allows us to close the lake water balance. This is basically accomplished by monitoring lake level changes combined with assumption or measurements of lake bathymetry. A recent global scale study assessed seasonal changes in water storage of large lakes using remotely sensed data from multiple sources together with assumptions related to lake bathymetry. Although these lake volume dynamics provide useful data related to climate change and lake ecology, they cannot address the specific inputs and outputs that causes these changes. Thank you.